Now we're just going to go through a few more examples using these differentiation rules. Let's start with an exercise where we are just asked to find the derivatives for various functions. The first function is f of x equal to x to the fourth minus 4 over 3x plus root x plus 4x plus 1. The first observation is that we can rewrite 4 over 3x as 4/3 of x to the negative 1 and root x as x to the 1/2. So far I haven't changed anything, I have just written the same function in a different fashion. The reason why we do that is because we want to use the basic differentiation rules, which are that the derivative of a sum is the sum of the derivatives, the derivative of a constant multiple is a constant multiple of the derivative, and the power rule, which allows us to differentiate a power of the variable, something of the form x to the n, and we obtain n x to the n minus 1. This is precisely to apply this rule that I have rewritten 1 over x as x to the negative 1 and root x as x to the 1/2. So now we have a sum of different terms. Because the derivative of a sum is the sum of the derivatives, the derivative of f is going to be the sum of the derivatives of each term, and each term is a constant multiple of a power of the variable, so we can use the other two rules to differentiate those. So we obtain this answer for the derivative because the derivative of x to the fourth is 4x cubed using the power rule. And we pull out the power, decrease the exponent by 1 using this power rule. The derivative of 4/3 x to the negative 1 is going to be 4/3 multiplied by negative 1 x to the negative 2. Right? On one hand we use the constant multiple, on the other hand we use the power rule like before. The derivative of x to the 1/2 is going to be 1/2 x to the 1 minus 1/2. I'm sorry, x to the 1/2 minus 1, therefore negative 1/2. The derivative of 4x is 4, and the derivative of 1 is 0. X to the negative 2 can be rewritten as 1 over x squared, x to the negative 1/2 as 1 over root x, and therefore the derivative of the function is 4x cubed plus 4 over 3x squared plus 1 over 2 root x plus 4. Let's move to the second function. We have x squared plus x plus 1, all this divided by x. We could think of that as a quotient and therefore try to use the quotient rule. However, you should notice that in that case this is a quotient that can be simplified quite a bit. If we observe that x squared plus x plus 1 over x is nothing but x squared over x plus x over x plus 1 over x, we obtain x plus 1 plus x to the negative 1 because x squared over x is x over x is 1, and 1 over x is x to the negative 1. So far I haven't changed anything, I have just rewritten my function differently. But now I can use the same rules as before, and I obtain for the derivative 1 for the derivative of x, 0 for the derivative of 1, and negative x to the negative 2 for the derivative of x to the negative 1. Therefore I obtain 1 minus 1 over x squared. For the third function, I have a similar quotient, x squared plus x plus 1 divided by x plus 1, but this time I cannot simplify like before. So it is a genuine quotient and I have to use the quotient rule. Here is the quotient rule. We differentiate the top, multiply by the bottom unchanged, subtract the derivative of the bottom, multiply by the top unchanged, and divide all that by the square of the bottom. In our case, this is what we obtain because the top in red is x squared plus x plus 1, the bottom in green is x plus 1, and so we have the bottom unchanged in these two places, which corresponds to these places in H prime, and the top unchanged here, which corresponds to this term. And now the two terms that remains to be calculated are f prime of x, the derivative of the top. The top here is x squared plus x plus 1, so the derivative is 2x plus 1. And what the only term remaining is the derivative of the bottom, g prime of x, derivative of the green term. But in our case it's x plus 1, so its derivative is just 1. Finally, if we look at the fourth function, we have a product of two factors. Therefore, if we don't want to have to multiply things through, we should use the product rule. The product rule tells us that if I want to differentiate a product of two factors, I differentiate the first factor, multiply by the second unchanged, then add the derivative of the second factor, multiply by the first factor unchanged. So in our case, the first factor in red is x squared plus root x cubed plus 1. And the second factor in green is 2 plus 2x plus x to the fifth. So to differentiate that, I can take the derivative of the first factor multiplied by the second factor unchanged, so this is the green term, 2 plus 2x plus x to the fifth, and then I have the first factor unchanged, x squared plus x to the 3/2 plus 1, that I will multiply by derivative of the green factor. So the term we need to calculate are derivative of the first factor, that's the derivative of this term, x squared plus root x cubed plus 1, and what we obtain is 2x plus 3/2 x to the 1/2. The reason is that the derivative of x squared is of course 2x, and root x cubed can be rewritten as x to the 3/2, and therefore its derivative can be obtained using the power rule, and it gives us 3/2 x to the 3/2 minus 1, in other words 3/2 x to the 1/2 for the derivative of root x cubed. The remaining term here is the derivative of the green factor, the second factor. In other words, derivative of 2 plus 2x plus x to the fifth. Derivative of 2 is 0, derivative of 2x is 2, and of x to the fifth is 5x to the fourth according to the power rule. So this is the derivative of the second factor. Now let's take a look at another kind of application. We want to find the tangent line to the graph of the function f of x defined by 2x squared plus x plus 1 divided by x minus 2 at the point of first coordinate x equal 1. This tangent line, according to what we have seen before, is going to be the line of slope f prime of 1 through the point of coordinates 1 and second coordinate f of 1. So to obtain the second coordinate of the point of tangency, it's f of 1, we simply plug x equal 1 in the function. In this case, we obtain 2. To find the slope of the line, we need to calculate f prime of 1. The first step is to calculate f prime of x. And because we have a quotient, we use the quotient rule. So we have derivative of the top. The top is 2x squared plus x plus 1. So the derivative is 4x plus 1. We multiply by the bottom unchanged, 4x minus 2. Then we subtract the derivative of the bottom, which is 4, multiply by the top unchanged, and we divide by the square of the bottom. To obtain the slope, we need to plug x equal 1 in this expression, and in this case we obtain negative 3/2. In other words, the line that we are considering is a line of slope negative 3/2 through the point of coordinates 1, 2. The equation of this line is y minus 2 equal negative 3/2 of x minus 1. As a final example, let's consider a particle that is moving along a straight line with law of motion given by the function s of t is t cubed plus t plus 1 multiplied by 1 minus root t. So this is the position of the particle at time t, where t is a time measured in seconds, and s is the position measured in meters. And we want to know the velocity of this particle after 4 seconds. According to what we have seen, the velocity after 4 seconds is simply the derivative of the position function at time 4. To calculate that, we're first going to calculate the derivative function using the formulas that we have seen. In this case, the function is given by a product, so we use a product rule. We have derivative of the first factor, so that's derivative of t cubed plus t plus 1. That gives us 3t squared plus 1. We multiply that by the second factor unchanged, 1 minus root t. Then we add first factor unchanged, multiply by derivative of the second, which gives us negative 1 over 2 root t. The reason is that root t is t to the 1/2, so its derivative is 1/2 t to the negative 1/2, which can be rewritten as 1 over 2 root t, as we have seen in previous examples before. Now what I'm looking for is not s prime of t, but s prime of 4. So I simply plug t equal 4 in this function. After simplification, we obtain negative 265 over 4. And this is, of course, in meter per second. So this is the velocity that we're looking for. Now you should be ready to take the quiz.